Hey, good morning, everybody. Here are your notes for section 3.7, and it's going to be on optimization. And there isn't going to be any new calcula formulas or rules. It's just going to be utilizing what we already know to find an optimum value for a situation. And by optimum value, they mean a min or a max. So we're going to basically be creating a function and trying to find a min or a max on it. Just to recap where the mins and maxes can occur on a function, if you had a graph of a function, let's say it was doing something like this, where can all the min and max values occur? So we know that they could occur at the critical numbers. So this would be where the first derivative was 0, or in some case undefined, if it was a sharp turn. So we're going to be looking where the first derivative is 0 or undefined. Those were our critical values. And then we also need to sometimes examine the endpoint. So you could get, for example, this endpoint right here is at the lowest point. That's a min. And this endpoint here is technically the max. So these would be the absolute min and the absolute max. These would be this would be a relative min, and this would be a relative max. So we're basically going to be examining the critical numbers where the first derivative is 0 or undefined, and in some situations you'll need to consider the endpoints of the interval that you're working on to see if that is a min or a max value. And let's go ahead and do the example that is in the note packet. So here's our example. It says we want to design an open box. So it's going to be an open box that has a square base and a surface area of 108 square inches. Find the maximum volume. So we're going to be trying to maximize the volume function. So we want to find a max on the volume. The restriction is that we only have so much surface area to work with. So whatever material you're building with, whether it's cardboard, wood, sheet metal, you have enough material or surface area of 108 inches squared. So let's go ahead and make a sketch of this situation. So let's say we have a open box. The fact that it's a open box is kind of key because they're telling us by it being open that it doesn't have a top. So it only has a bottom. It's just an empty space. There's no lid on it, basically. They did say it's going to be a square base. So whatever the side lengths are, they're going to be the same, and then it's going to have a height. So if we wanted to represent the volume, since that's what we're trying to maximize, so the volume would be the base area times the height, or x times h. So x squared times h. And we're going to be looking to find a max on this. However, to get to the point where we can find a maximum at the critical values, where the first derivative is 0 or undefined, we want to get it expressed in less variables. Right now it's expressed as a function of x and a function of h. So we want to get it all switched over to just one variable. And we also have the restriction of 108 square inches. So we're limited by having a surface area to work with of 108. If we had as much surface area as we wanted, then we could make the box bigger and bigger and bigger. So our limit is going to be a surface area of 108. So we're going to need an equation that describes the surface area. So the surface area is, one of the surfaces is going to be the bottom surface. That's going to be x by x, or x squared. So we have that bottom surface. That's going to be x squared. We don't have the top surface. We don't have a lid on it. If we did, it would be 2 times x squared, because you'd have a top and a bottom, plus the surface area for the walls. So if you look at this wall, like on the right hand side, that's going to be x by h. And then you're going to have 4 walls going around. You're going to have the back wall, the left hand wall, and the front wall. So you're going to have xh times 4. So you're going to have 4xh. And how much surface area do we have to work with? 108. So capital S is going to be 108. And that's going to be our equation for our surface area. What we're going to do is we're going to use this equation to solve for one of the variables and substitute it into the volume equation so we have less variables. So let's go ahead and solve for variable h. We'll get a definition for h, and once we have that definition we can plug it into h over here. So to solve this we're going to subtract by x squared. And then divide by 4x. So h, let's clean that up a little bit. So h is going to be 108 minus x squared, all divided by 4x. So this definition for h can be substituted into h in our volume equation. This is the equation that we're going to be trying to maximize, so we're going to be looking for the first derivative on the volume. So we'll say the volume is going to be x squared multiplied by h, and h is going to be 108 minus x squared, all divided by 4x. So there's our volume as a function of one variable x, and we're going to be looking for the first derivative to see where it's 0 or undefined. That's going to be our critical points where we can have a min or a max, but we're not going to want to derive it when it's in this form. This is kind of a mess. So let's simplify first, and then we'll take the derivative. So we have x squared over 1 essentially. So we could distribute. So distributing in the x squared, so we're going to bring this in. We're going to get volume equals 108 times the x squared, and distribute it to the second term. That's going to get you a minus x to the 4th. All over 4x. And everything is being divided by 4x, so we could say the volume, and this is technically a function of x now. You could call it v of x now. Back earlier it was a function of x and h, so it was not a function of just one variable. Now we have the volume as a function of one variable. So if we divide everything by 4x, 108 divided by 4, that should get us 27. And x squared divided by x, that's going to simplify to just x to the first power up top, minus 1 over 4. And then simplify your x's, x to the 4th up top, divided by x down bottom. That's going to leave us with x to the 3rd. So now we have a volume model that's a little bit simpler to work with. We're looking for v prime. So we want to find v prime because we know that mins and maxes can occur where the first derivative is 0 or undefined. So let's find v prime. So the derivative of 27x should be 27 minus 3/4, drop it down a power to x squared, And once we have our first derivative, we know mins and maxes occur where it's 0 or undefined, the critical numbers. So set it equal to 0. And that's going to get us 27 minus 3/4 x squared. And let's solve this, so subtract 27. And multiply by the reciprocal. And we're starting to run out of room here. So we got a negative times a negative, that's going to be a positive. 27 divided by 3, that's going to get you 9. 9 times 4 is 36, so x squared is going to be 36. So let's see if we can fit it in here. Which means x is going to have to be plus or minus 6. So you're going to have two critical values, at positive 6 and at negative 6. So mins and maxes could occur at where x is either plus or minus 6. So here's our critical numbers. Which one makes sense in terms of this particular application? It wouldn't make sense to have x be a negative dimension. So we're essentially just looking at where x is 6. And right about now is where we need to kind of start considering the feasible domain for x. So what are some reasonable dimensions for x? So if you go back to the original question, they did say kind of think about the feasible domain. So what would make sense for x for this particular box? As we start to kind of look at our different possible x values, if the height is changing, getting taller or getting shorter, what's going to be kind of the extreme values for h? So let's say h was getting as small as possible. So h was getting shorter and shorter and shorter. Then all of your surface area, all of the 108 of surface area that we have to work with, would basically be all contained in the base down at the bottom. So if you had no height, all of your surface area would be the flat piece that is left over down at the bottom. So what's the largest that x could be in order to make all the surface area be down bottom? So that's going to have to be x squared would be working out to be 108. So x itself would have to be the square root of 108. So if you had no height on this box, then x could not be any larger than 108. And then thinking of it the other way, what if it was a tall, skinny box? So what if x was going to 0? If x was going to 0, then you wouldn't have a three-dimensional object either. So the smallest that x could be is 0. X is not going to be 0, and it's not going to be a negative number. So your feasible domain for x is going to be between 0 and the square root of 108. For geometric problems, you usually don't need to worry about the endpoints of the function, because by the time you get to the endpoint, you no longer have a geometric or three-dimensional figure anymore. But if it was a different type of application, if it was a money problem or something else, so if it was something else besides a geometry problem, then you might need to check those endpoints. So let's just kind of go through the procedure. So we know we could have a min or a max at a critical number, and we also know that mins and maxes can sometimes occur at the endpoints. So we're going to need to check all these. So we're going to do a input-output table. So what are the possible x values, and what do we get for a volume at that x value? So if x was 0, that's going to be kind of the endpoint for this particular box, and if x was the square root of 108, then that is going to be the other endpoint. And what are all the critical numbers that exist in between? We just had one critical number in this case, so we only need to test one potential min or max, and that's going to be where x is 6. And then you want to take these x values, plug them back into your volume model, so plug them back into v of x, and see what you actually get for a volume. So if we did v of 0, go back to a volume equation that is kind of the most convenient to work with. So you could maybe look at this one, so this simplified one. So if we put 0 in for the volume equation, remember we're not putting it into the first derivative because we already know it's going to be 0 when x is 6. So we want to know what the volume is when x is 0. So put it into your volume equation, and that's going to get you 0. If we put in v of 6, then that is coincidentally going to get you 108. So again, if we went back to this volume equation and put a 6 in for x, then that's going to get us 108. And if you put in the square root of 108, then again, when you have the square root of 108, your h is basically 0. You have no more height, so we could assume that that's just going to be 0. You could also go back to the volume equation, and if you put square root of 108 in there and actually calculate that out, that is going to get you 0. So we didn't get a min or a max at an endpoint, we actually got our max at the critical number. So when x is 6, you're going to maximize your volume. For this packet, I think a lot of the problems are geometric problems, so you're going to be finding the mins and maxes at the critical numbers. You're probably going to develop kind of bad habits and not check the endpoints, but if it was a different type of problem, you would definitely be needing to check those endpoints also every single time. So the question was, back to the original question, what are the dimensions of the box? So we know that x is going to be 6. We know this other dimension x is going to be 6. And then we just have one more dimension, h. So we're going to need to find that third dimension, h. So to find the third dimension, you want to go back somewhere in the work where you have a definition of h, which the easiest place would probably be right here, where we have a definition of what h is in terms of x. And put a 6 into your x value, since we now know that x is going to be 6. And calculate that and find the h value. And if we calculate the h value for when x is 6, it should work out to be 3. So our 3 dimensions, it needs to be a 6 by 6 by 3. So let's find a place where we can write that. So it's going to be a 6 by 6 by 3, and the units on this are inches. So to maximize the volume of that box, you would want to build it so it has the dimensions of 6 by 6 by 3. And that is the example for this packet, packet 3.7. It's on optimization. It's basically finding mins and maxes. And we know that mins and maxes can occur where the first derivative is 0 or undefined, or in some cases at the endpoint. So you want to find your critical numbers, test your critical numbers for mins and maxes, and then also in some cases test those endpoints.